So today we're going to look at Charles's law, and Charles's law deals with the volume and temperature relationship of gases. So in the images on the screen right now, you have the kind of complete opposite images. So one is where you're increasing the heat and the volume gets bigger, and the other one was where you're removing the heat by adding the liquid nitrogen there and cooling things down, and the volume gets smaller. So we can see that temperature has a huge impact on the volume of a gas. So Jacques Charles was the guy that we're talking about, and he found that there is that relationship between temperature and volume of a gas takes up. And what he did was he trapped gas into a cylinder with a movable piston, almost kind of like a syringe or, like I said, just a cylinder with a piston inside. So you can think of that we're going to use syringes in class to represent this. And he took that cylinder and put it into a water bath, and he changed the temperature, heated it up, cooled it down, and saw what happened to the volume. And he found that as the temperature was increased, so did the volume. And the thing that we should note here, this time, we already learned that pressure and volume are related, so now we need to hold the pressure constant, and as well as that, we need to hold the amount of gas constant, because we want to just see how the temperature is affecting the volume. So the container has to be able to expand or contract, so it kind of looks like something like this, where you have this movable piston. And if it was completely frictionless, there was no forces, it would be just strictly the gas that's allowing that volume to rise. The pressure that's pushing on that piston will be constant if you're doing this in the same room because it's the same same atmospheric pressure around. So we're holding pressure constant, we're holding the number of particles constant, we're just changing the temperature and seeing how it affects the volume. So when you do that, you get a graph that looks something like this. It's a nice straight line, and you notice that the slope is positive. Why is it positive? Well, if one is going up, the other one's going up. If one of them goes down, the other one goes down. So they rise and fall together. And that straight line of positive slope tells us this is a direct proportion or a direct relationship. So we learned that Boyle's law was an inverse relationship, whereas one goes up, the other one goes down. This one, it's direct because they both increase or decrease together. So he wasn't able to get super low temperatures, but what you could do, what Charles did was he took his graph. So here's a bunch of data. He basically tried different gases, different amounts of gases, and varied their temperatures and plotted those data points. So you get these data points, and he created a line of best fit, but then we extend that line. And when we extend that line, we call that extrapolation. So you're extending your data past the data you've measured. So you're going outside or outside of the data that you have. If you wanted to figure out what a point was like here, that would be interpolation because you're going inside the data points you have. But going outside is called extrapolation. And so when he did that, he extended all those lines, and if you notice, because of the different slopes of those lines, they all end up hitting the x-axis at the exact same temperature. And the neat thing about that temperature, this would be a temperature where the volume of the gas was actually exactly 0. And that temperature kept coming out at minus 273 degrees Celsius. Now, if you assume that our gas didn't go from gas to solid to liquid, and you just kept cooling it and cooling it, cooling it, if it didn't liquefy, what we're saying here is that the volume of the gas would be exactly 0. So there would have no volume at negative 273 degrees Celsius. So what he figured is that this has to be the lowest possible temperature because you can't get to negative volumes. That's not possible. So this would have to be absolutely the lowest possible temperature possible, and that number ends up being negative 273.15 degrees Celsius. We'll just round it off to 273. Now, can you have 0 volume? No. If you have matter, it has to have mass, and mass takes up space. But some really funky things start happening at super cold temperatures. So I'm going to leave it at that for now. But at the end of the day, the idea at this point is all molecular motion would stop at absolute 0. So another guy by the name of Lord Kelvin, or William Thomson, he dubbed himself Lord Kelvin. He reasoned that at absolute 0, all that motion stops. So in other words, if you have 0 motion, that would mean that you have 0 energy. So why are we using a Celsius scale or a Fahrenheit scale where we have positive and negative temperatures? Why don't we just say that the temperature scale, since it's measuring energy, starts at 0 energy and works its way up? So what he did was he basically created a new temperature scale. Really, it's Celsius' scale, but he just backed it up by 273 degrees Celsius. So our 0 on the Kelvin scale is negative 273 Celsius, and then every degree is the same. And so that makes absolute 0, 0 Kelvin. And notice he doesn't put a degree symbol beside his. I always think that he thinks he's kind of a big deal because he's Lord Kelvin. He doesn't need a degree symbol like Celsius did. And the advantage of this scale is that we don't have negative numbers, and this is going to help us with our relationships because of the direct relationship. Negative numbers are not going to allow it to work very well. So if you imagine our 3 temperature scales that we will be familiar with by the end of this, we've heard of Fahrenheit. We don't use it in Canada very often, but water freezes at 32 and boils at 212. Absolute 0 would be negative 459 Fahrenheit, and that's a weird scale that we don't really care about all that much. But the Celsius scale, what we're familiar with, 0 is where water freezes, and 100 is where water boils, or temperature at which water boils. Absolute 0 would be negative 273. So now, instead of going into these negative values, why don't we just say, well, we're going to move the zeros to there. So that makes the freezing point of water 273 Kelvin and the boiling point of water 373 Kelvin. And the way I remember how these two scales are related is, again, I think that I always think about Kelvin as being better than everybody else because he thinks he's Lord Kelvin. So he thinks he's better than everybody. So his unit is always going to be 273 more than Celsius. Or Celsius is always going to be 273 less. So if I wanted to take, for example, 25 degrees Celsius and convert it to Kelvin, Kelvin's higher. So I'm going to add 273. So that makes 298, and the unit is Kelvin. No degree symbol, just Kelvin, capital K. 50 Kelvin to Celsius, so I'm going to take away, because Celsius is worse than Kelvin, so I got to go below Kelvin. So I'm going to take my 50 Kelvin and subtract 273, and I get negative, so I'm going to subtract 273, and I get negative 223 Kelvin, capital K. So again, Kelvin's higher than Celsius. Celsius is lower than Kelvin. Or sorry, and this should have been Celsius. I lost my train of thought there. That should be Celsius because we're going to Celsius. Okay, so now that we've learned how to convert the Kelvin scale, we can actually do Charles' law because it only works with the Kelvin scale. We need our temperatures to always be positive values for this ratio to work. So here's Charles' law. The volume of a gas varies directly with temperature in Kelvin if the pressure and amount of gas are constant. So we learned that with an inverse relationship like Boyle's, we did P times V equals K, equals some constant. That's an inverse relationship. But with a direct relationship, it's a little bit different. This means that the ratio of your volume and temperature have to be constant. So instead of it being divide to get constant, now it's multiply to get constant. Now it's divide to get constant. So if we take one volume and divide it by its temperature, we'll get a number. And we take another volume and divide it by its temperature, we'll get the same number. So since these two things both equal K, we can say that both of those things are equal to each other. And then here's Charles' law in a formula format. Now, V is volume, and it can be measured in any volume measurement, liters, millimeters, cubic centimeters, whatever, but temperature must be in Kelvin. Okay, that's the first thing we need to do with any questions we do in this part of the course, is we must convert to Kelvin. So let's go ahead and we'll do a couple of example questions. So if we're reading this, again, I'm going to do the two different ways. I'll do formula method and logic method, and it just depends on which you're more comfortable with. Either way is fine. Logic is a little bit quicker, but either way is fine. So it says if the temperature of 6 liters of gas at 25 degrees Celsius is increased to 227, determine the volume at the new temperature. So the first thing I'm going to do before anything is I'm going to change these to Kelvin. So I'm going to cross this out. 25 Celsius is 298 Kelvin. And then 227 Celsius is 500 Kelvin. All right, so now what we're going to do is we're going to write our equation if we're going to do the formula method. So V1 over T1 equals V2 over T2. So now we should figure out which one's which. So we're starting at 6 liters and 298, and we want to find the volume at 500. So this is going to be my V1, this is my T1, this is my T2, and we're trying to find V2. That's a question mark. So we substitute those values in. So we have 6.0 liters over T1 is 298 Kelvin equals V2 we're trying to find, but T2 is 500 Kelvin. So if I rearrange and solve for V2, basically I'm going to multiply both sides by 500 Kelvin. Right, so these cancel. So V2 will be 500 times 6 divided by 298, and you should get an answer of V2 equaling 10.07, and the units will be liters, because that's the units that are left, because kelvins are gone. Okay, so now again, stop, ask yourself, does this make sense? The temperature went up. So if temperature goes up, the volume should go up. The volume was 6, now it's 10. That makes sense to me. So now if we're going to do the logic method, what I would do is I'm going to start with the volume I'm given, which is 6.0 liters. And we know that the temperature is rising, which is basically what we just said. So that means that the volume must rise. So I'm going to multiply the 6 liters by the temperature ratio that makes it go higher. So 500 Kelvin goes on top, 298 Kelvin goes on the bottom. Notice Kelvins cancel, and it's still 6 times 500 divided by 298, so it's the same answer, 10.07 liters. There's your answer. All right, let's do another one. So it says if the volume of the gas at 73 is doubled to 48, calculate the final temperature in Celsius. So first things first, before I worry about anything, let's change that negative 73 to Kelvin. So negative 73 is the same as 200 Kelvin. I want to do that first before I forget. It wants me to find the temperature in Celsius, but we'll find it in Kelvin, then we'll convert it back at the end. So we are starting with some sort of volume, and we're doubling it to 48. And the starting temperature is this. So this would be V1, this is T1, and this is V2, and we want to find T2. Now, they didn't give us V1, but they told us that it was doubled to 48. So to go back would be half. So V1 would have to be 24 liters. So we can set up our equation. V1 over T1 equals V2 over T2. Substitute our values in. 24 liters over 200 Kelvin equals V2, which is 48 liters, over T2. So if we were going to rearrange and solve, so now this is where lots of students get hung up, is the solving for T. T is in the denominator right now. If we're using formulas, you can't solve for T when it's in the denominator. We want, anytime you're trying to solve for an unknown, you want it to look like that. The unknown equals something. But if I got rid of that 48, it would be 1 over T2. I can't do that. So we're going to multiply both sides by T2 to get it out of the denominator. So what ends up happening is this. So you'll end up with 24 liters times T2 over 200 Kelvin equals 48 liters. And now at this point, now we're going to rearrange, because T2 is now on the numerator. It's T2 is equal to something. So we're going to get rid of the 200 by multiplying both sides by 200 Kelvin. And I'm going to do the 24 at the same time. I'm going to divide both sides by 24 liters so that the 24 liters cancel, the 200 Kelvins cancel. So what you're left with, if you take out everything that I just canceled, it would look like this. 48 liters times 200 Kelvin over 24 liters. So we punch those numbers in, and you should get a temperature of 400 Kelvin. Now, I use this question because it's easy numbers. If you think about what should have happened, the volume doubled. Well, that means the temperature should have also doubled because they move up and down together. So if you double the volume, you double the temperature. Double the temperature, you double the volume. In Kelvin, though. So the temperature started at 200 Kelvin, it doubled to 400 Kelvin. That makes sense. So I set this all up correctly. If we want to change it to Celsius, which is what the question asked for, Celsius is 273 worse than Kelvin. So then that would end up being 127 degrees Celsius. So now, if I was doing this logic method, I don't have to worry about solving for the denominator this time because I'm just going to set it up. So we know that the volume increased. So that would mean the temperature would have to increase. So we're going to take our initial temperature in Kelvin, 200 Kelvin, and we're multiplied by the volume ratio that makes it go up. So 48 liters would go on top and 24 liters goes on the bottom. And if you look, it's exact same math. So you end up with 400 Kelvin. And then we take away 273 and you get 127 degrees Celsius. So either way, if you're going to do logic method though, I do want you to state the relationship because that's where we're getting this ratio from, telling whether I have to make it go up or make it go down. So you can pause the video at this point. There are some try these ones, give them a shot, and then I'll have the worked out solutions for you in a second. So pause the video now, give the next two questions a try, and then I'll work through them. So with this one, we have a gas inside the cylinder, and it's got a movable piston. The volume is 0.3 liters at 25, and we want to know what it will be when it's 315. So again, I'm going to break this up. First thing I'm going to do, change to Kelvin. So 315 Kelvin is the same as 588. Sorry, 315 Celsius, the same as 588 Kelvin. And 25 is 298 Kelvin. So now that I've got my two temperatures in Kelvin, now we're going to set up our equation. So V1 over T1 equals V2 over T2. So it's heated to this, so that would be my new temperature. It was 0.3 liters, so that's my initial temperature. This is my first temperature, or sorry, first volume, first temperature. And we're going to solve for V2. So substitute my numbers in. 0.3 liters over T1, 298 Kelvin, equals V2, we don't know. T2 is 588 Kelvin. Solve for V2, so we're going to multiply both sides by 588 Kelvin. So cancel, cancel. So V2 is going to equal 588 times 0.3 divided by 298, which is 0.59 liters. There's our final answer. Again, ask yourself, does this make sense? Temperature went up, volume should go up. That makes sense. So again, same thing over here. We're going to say, well, the temperature is going up. So we got to make the volume go up. So I start with my volume, 0.3 liters, and I'm going to make it get bigger. To make it get bigger, I put the bigger temperature on top and the smaller temperature on the bottom. So same math, same everything. It ends up being 0.59 liters. So same answer. Okay, we got one more to do, and this one's a little bit different. So when you're going hot air ballooning, or when they're filling up a hot air balloon, they don't fill it full with air. They just blow some air into it, and then they heat that air because the air will expand. If you filled the balloon full and you started heating it, it would actually rip the balloon and you'd fall out of the sky. So that would not be good. So they would have to actually take all these things into account, the temperature, the pressure, all this kind of stuff, because they don't want the balloon to overinflate because it would be devastating. So they're out on a cool morning, it's 10 degrees Celsius out, they start filling their balloon. When the balloon is 3/4 of the way full, that's when they start to heat it. So they don't fill it full, they fill it partway full, and then they heat it from there. We want to know at what temperature will the balloon be filled to capacity, because we wouldn't want to go over that temperature. So the air is starting out at 10 Celsius, but again, we're going to change this to Kelvin, so that's 283 Kelvin. I'm going to do that right away. And the balloon's capacity is 1,700 meters cubed. That's the maximum volume of the balloon. Now, we don't know the starting volume right now, but we can figure it out because we know that they started with the volume at 3/4 full. So what I'm going to do is I'm going to take my 1,700 meters cubed and I'm going to times it by 3/4, or in other words, or 75%. And what ends up happening is we're going to figure out how much air they put in the balloon to start. That's 1,275 meters cubed. So this would be my V1. This is my T1. This is my V2, and they want to find T2. So we're going to find that temperature in Celsius. So again, we'll do both methods off to the side. So V1 over T1 equals V2 over T2. Substitute our values in. So V1, 1275 meters cubed. T1, 283 Kelvin. V2 is 1700 meters cubed. That's our max volume. T2, we don't know. So again, we have to multiply both sides by T2 to get it out of the denominator. So cancel, cancel. So you end up with T2 times 1273 meters cubed over 283 Kelvin equals 1700 meters cubed. So now we are going to divide both sides by 273 meters cubed and times both sides by 283 Kelvin. So T2 is going to equal 377.3 Kelvin, and we're going to take away 273, and that gives us 104 degrees Celsius. Now, if we're going to do this logic method, we know that the volume went up, so the temperature has to go up. So I'm going to start with my initial temperature, 283 Kelvin. I'm going to multiply by the volume ratio that makes the temperature get bigger. So 1700, times by 1700 meters cubed divided by 273 meters cubed, and we still get 377.3 Kelvin. Take away 273 is 104 degrees Celsius. So we want that balloon to get over 104 degrees Celsius.